the uh, questions. Any questions about last time? So there are your functions, compositions, and inverses, and so we'll put that behind us. I think we covered mostly everything. We'll see how well it went, judging by your due Friday night. Okay, Friday night, and we'll just we'll continue on with the topic that is the not a review anymore. So that is a review, and that topic is the sequences. Okay, so that's what we started on Tuesday with sequences. So it is kind of a step back in the sense that it's simpler than functions. Okay, so if you think about it, this kind of simple picture, the side by side a function y equal x squared on one hand, and another one y is equal to n squared. Well, fine. Okay. So in other words, this is really very familiar situation, right? It looks like this. Let's say we only concentrate on the positive values. Okay, y. And then this is a sequence. What's the difference? You've seen sequences already. It will have n will be running through, say, 0, 1, 2, 3. So the only values that are allowed are integers. Okay, that's the main difference. 1, 1, 0, 0, 1, 1, 2, 4, and then there's 1, 1, 1 over here, 3, 9 or something like that. So it'd be more for this. So 1, 2, 3, 0. So 3 inputs, 4 outputs. So these are ands, and as you can see, the ladder has less information. So you certainly can go this way, and I would call it sampling. Okay, so literally what you do with any kind of process or quantity that changes with time, or just changes with a variable x, you sample it by just taking not all the values, but at regular intervals. So you sample your location, you sample your speed with the speedometer, write it down, okay? And as long as that is done in regular intervals, more or less, ideally, what you end up with is a sequence. Okay, so then you can do better your sampling, and the more frequent, the better approximate your function is approximated. So like I said, if we have a continuous process, motion, the presumption is that if we're moving from this point to that point, we have visited every point in between. Okay, that's the assumption about any kind of motion and about other things. And so then we sample it in order to be able to deal with it quantitatively. So as we did last time, on Tuesday, you can plot. This you can plot easily, and that's what either Excel or your graphic calculator, that's what it does. So let's do Excel as a last resort, because they might start interfering with each other. So that is one thing. It's a continuous process, either really continuous or simply continuous, and then it is sampled. Okay, and then you have a sequence. And alternatively is what we just started with in those two examples, when they are truly, a sequence is truly discrete and incremental, and there is no continuous process behind it whatsoever. So every month you add $100 to your bank account, okay, and it goes up, and on and on. So in that again, we started separate. Just to make this picture complete, what about backwards? If you know what this term, you know the term?
The inverse.
What?
The inverse.
No, 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 I'm talking about going, so the sampling is from continuous function with continuum, like you think of it as a rope, um, and then what we sampled it, and we ended up with a bunch of points, entirely disconnected. Okay, that's sample. Okay, so the result might be, we did it exactly that with itself, which the behind those data points as well as the chart is a formula. And the formula say y equals x squared is applicable to any x, right? Any x you plug in and you have, that's why you have infinitely many points. The graphic calculator plots everything and it gives you the impression that it's continuous. Okay, so that is the assumption. But behind it is just a bunch of points that are just so close to each other, just like on TV that they seem continuous, just like a video also, which is made of frames, but it's so close to each other that we don't see the difference and everything looks continuous. Okay, so but behind it is sample. So that's one way to study things, but I just want to, what can happen is the opposite in a way. You don't have a function of, there might be a function there, but you don't know what it is. Okay, so you have a bunch of points, and you want to produce. You see the second arrow from right to left. You have a bunch of points, and we want to connect them into a curve. Anybody knows?
You graph it.
What?
You graph it.
There is nothing to graph. You see, that's the point that we want to find the formula. There's a bunch of points, and we want to find the formula as y equals x. So for example, that's the way I arranged it here, so that actually that curve on the left actually passes, somebody is left-handed, and they move the, somebody left-handed now. So what you can do here is you see this. I put these two together. How should I put this? Put it this way. We do the points. And this is the curve. The blue curve is this. But they're the same. We do jumps back and forth, back and forth. Okay. Click. Where? Okay. So it's the same thing. Okay. Maybe not entirely. Entirely to the scale, but as you can see, that is the point. That is the sampling. So out of a continuous curve, we cut 4 or more points, and that creates a sequence. Backwards, the word is actually interpolation. So if your information is limited and there are gaps, you fill the gaps, and that filling the gap is called interpolation. There's also the word extrapolation, which is goes beyond your, not in between points, but beyond the point. So that might come up later, but not right now. Right now, we are trying to abandon for now the functions, which you may have seen elsewhere for a while, and just concentrate on something simpler, and that is sequences. And beginning with sequences not like this that you require for sequence sampling, which is really straightforward. I mean, you look at it, it's the same formula, y equals x squared, y equals n squared. It's the same thing. You just have a different name for your variable. That's all. So, but rather, as you can see in these two examples, the sequence is produced through recursive definition. So you know the current state of affairs, and you know what's going to happen next. So let me look at these two examples one more time, and then we'll have more. Okay, so example 1, add $100 every month. With this is the crucial question is what did you have, say, in January? Nothing. So you start in January and then start to add $100 every month. So this is how we started this. There's notation to be taken care of. So we have a sequence sequence of numbers, which is technically is infinite. So in real life, certainly you cannot continue forever, but if you want to study what's going to do in the future, you can just as well assume that it is infinite, and then you see if there is any kind of trend. Okay, so it is infinite in one sense. Either the correspondence to the months, so I have to put months here, and then it runs from 1, 2, 3, 4. Okay, on and on, dot, dot, dot. And then the amount. You can certainly do it by hand, say you can do it by hand, and so in January, assuming this is January, you add 100, then add one more, and on and on. This is your sequence. So this is because the sequence is so simple, then we don't really necessarily would have to do anything else with it because it's so predictable. But we just have to introduce notation so that we can handle more complex situations. So this is how we record it. A sub n. Okay, well let's just start with a sub 1. A sub 1 is equal to 100, A sub 2 is equal to 200, A sub 3 is equal to 300, and so on. Okay? So you can notice the difference from the functions where the variable is inside the parentheses. So say you have f of x is equal to, say, x squared. Okay? So it's the same story here. This is the variable. And as far as the notation on the left is concerned, the f is the name of the function, x is the name of the variable, and you plug in the values in what sense. Say f of 0 is equal to 0, f of 1 is equal to 1, f of 2 is equal to 4, and so on. That's how you write it. A very similar situation. But now we are talking about sequences, and therefore there is nothing in between. That's the difference. The difference primarily lies in the fact that between if we're talking about functions f of x equals x squared, we are talking about possible. There are no gaps necessarily. So we could assume that there are no gaps, and for that particular function, there is definitely no gap. Okay, so f of 0 is equal to 0, f of 1 is equal to 1, but there is more, so I can insert as many as I like. I have f of 1/2 is equal to 1/4. Okay, and so on. So in every, there are no gaps, and we can fill those gaps with more and more values. That's the continuum. That's what's called the continuum. This infinitely divisible entity. Okay, and that makes things complicated. So we're looking for a tool that is simpler, and that's why we look at sequences. And the sequences, there are gaps. It's made of gaps, nothing but gaps. So there is between A of 1 is 100, A of 2 is 200, and there is nothing in between. Okay, there is nothing whatsoever in between. In between, and this is the only incomplete part is on the right. Okay, so how far we can go, and we don't know if we go on 42 many steps, we'll have to take care of it. But otherwise, these we can actually put it in the form of a list like this, or we ultimately might come up with a formula. At this point, we do have a list, but it is incomplete, right? So no list is complete, and that's why you want some kind of formula. Okay, so let me, however, write out first the recursive definition. The recursive definition of this sequence is comes from the original statement. Add 100 every month with every month. Okay, so this is what we do. So this is what we do. We suppose A1 is equal to 0, sorry, 100. And then AN plus 1 is equal to AN plus 100. Okay? So remember once again, this subscript, this N, it indicates the month, the number of the month since that January. Okay? So N plus 1 is the next month if N is the current month. So what is the amount of money in the next month is the current amount plus 100. So that's the recursive definition of the sequence. Okay, because the change is incremental, all we have to describe is how we change from the current to the next. Okay, so that's a very simple situation. The formula is straightforward. And very frequently, this is the way we face what we have, and sometimes we are not in a position to find anything more than that. But this one is so simple that we can actually find direct or explicit formula. Okay. Discrete or explicit, the direct or explicit formula is just like the function of the right. It is if you know the month, you should know the amount of money. Okay? So in other words, we are expressing the amount of money after n months in terms of n. So express, this is it is to be found. So this is it's not the definition anymore. The definition is recursive, based on that verbal description that we had originally. And now we want to explicit formula. You want to know exactly, say, after 100 months, how much money do I have? Okay, so express AN in terms of N. Okay, so that's what the formula is. So, what's the formula? 100 N. 100 N. You can certainly notice the pattern over there. A1 is 100, A2 is 200, A3 is 300. So once you do a few of those, you can actually guess what the answer should be. Or you can look at the definition, the recursive definition, and well, come up to arrive to the same exact conclusion. So after all, AN is equal to 100 N. AN plus 1 is equal to what? No. 100 N plus 1, yes. So you simply replace N with N plus 1, just like in your homework, that substitution operation, remember? So the variable is substituted with whatever value that we want to have. So that's the advantage of this formula. I could start plugging in N is equal to 100, or N is equal to 755. You just plug in and the computation is very directly, and you know exactly how much money you got. Okay, so this is once again the starting with frequently recursive indirect definition of your sequence. You produce direct explicit formula. Okay, so something that you don't have to face when you deal with functions, but frequently sequences are defined in this manner. Okay, so let's do the second example. Same situation. You, what was the 5% APR with, to be specific, say $100 in gain in the beginning. Okay, so that is once again is a verbal description of our sequence. So we first of all introduce the notation. So for example, this is the notation that I introduced. Let n be the year since the beginning. Okay, so I want to once again have a sequence that captures the amount of money I have, or will have, or I might have, if I follow this process of adding not adding any money to the account, just using 5% interest. Okay, so this is the notation, and AN, so that's number one, and number two, let AN be the amount of money after n months, years. Okay? So let's now take our description and write the recursive definition, following the idea from above. So what do I write here? Let me maybe move this more before I use different letters here. How about B? Okay, so B in the amount of money after n years. So what's the recursive definition? Right at the very top, similar to that. Now look at first. There are two items. What's the first? You can see. Let's do the first item first.
100% or $100.
Yeah, B1 is 100. Okay, and now we have to express how much money I have after n plus 1 years in terms of how much I have after n years. So we don't know how much we have. All we want is this definition back referencing to the previous amount. Okay, just like in this previous one. So we gain 5%. That's gain 5%. How much do I have? So if in the beginning I have $100, how much do I have after 585? So how did you compute it?
5% of 100 is 5.
Okay, well, can you think of a formula? 0.05, 1, so it is either it's a 100, right? So it will be the current amount plus the current amount multiplied by what?
1.05.
1.05, or taken together is 1.05 times Bn. Okay? That's the recursive definition. So in other words, the difference from the last example is that instead of adding a certain amount every time, mathematically speaking, instead of adding a fixed amount every time, we are multiplying by a fixed number. Adding fixed number versus multiplying by fixed number. Okay, so now we are just in the same same question is now, what about explicit? Explicit formula. In other words, Bn in terms of n. So after 1 year, I multiply by 1.05. After 2 years, I multiply by 1.05 one more time. Okay, after 3 years, I multiply by 1.05 3 times. What am I talking about?
The exponent.
It is the exponent, right? So that's the exponent. Multiplying 3 times by 1.25 is the same as multiplying by the third power of 1 or 1.05. Okay? Sounds familiar? The sequence, the exponents. Exponents is we'll look at it. It's not dissimilar from what we just saw. We did addition, right? Adding 100, and then we have one with multiplication. Why? Because multiplication is simply is an abbreviated notation for repeated addition. Okay? So if you add 100 n times, it's the same as simply multiplying by 100. Multiplying by n. N times 100. So add n 1 times. Add 100 n times. It's the same as add 100 times 7. Right? So, and we have this formula, 100 times 7. The same thing happens here, except the abbreviation of the repeated multiplication is exponent. Okay? So then bn rather, bn is equal to what?
100 times 0.05 to the n power.
That's right, 1.05 n power times, do we need one, times 100?
Plus
Well, yeah.
Plus 1. Yeah, well, that's another way to put it like this. Okay, so to make sure that we were not messed up in the beginning, so, no, hold on, no, it was okay actually. Hold on a second. Back.
What I said was 0.05 to the n. You just added that one in front of it to where it already.
No, we don't need that. No, we don't need. So when n is equal to 1, it should be minus 1. That's what I meant. Minus 1. Okay, so because in the beginning we're supposed to have 100, not 105, right? So it will be minus 1. Okay? So starting with n from 1 to 2, even though it's probably easy just to start with 0. N is our choice, right? Okay? So I'm the same here. I forgot to write it. Okay? So as you can see there, that's the explicit formula once again. If you do Excel, then it doesn't matter. It is in fact easier, just as easy to put in the recursive formula and it goes from line to line, from line to next to next to next, or you put an explicit formula. Okay. In fact, the one that the simulation that you saw, motion of planets on Monday, remember, it was done recursively because so you know your location and you know your velocity. Okay, then you find your next location. It's exactly like this, except the difference is you have more stuff going on. You have 2 sequences with respect to x and with respect to y, and they interact. And then there are forces and so on. So it's just more complicated procedure for computing this, but ultimately it's still a sequence. Okay, so so the sequence and then it inserted the image, the page in the middle, not in the end. Okay, so these are just examples, even though they're good to remember. They're also terms for terminology for these. This is called an arithmetic progression. Arithmetic. Okay, and this called, you can guess, well, maybe not, geometric progression. Another name that you may have heard for geometric progression is exponential growth. You can certainly see that multiplication is good because ultimately you're going faster and faster and faster because of the compounded interest. Okay, but since you only start with $100, then you have the first guy had $200 at the end of the first year, and you have only 105. Okay, so he's going to be ahead of you for a while, but after you prepare to wait long enough, this is what he is doing, and this is what you are doing with your compounded interest. You start with the same amount, but you're behind, like this. But then if you wait long enough, it might take a while, though, and then you will overcome the growth will be faster. But it could take you 100 years. Okay, so a little bit of terminology in order. So a sequence is a function with the domain, an interval, and an interval of integers. Such as interval starting with, say, p plus 1, p plus 2, p plus 3, and so on. So it is technically an array. So when you put it in the braces, it's an array. Okay, so we could start counting at 1, we could start counting at 0, or we could start -1, -5, and positive 500 in all sequences. Okay, so the notation is usually like this. This is the abbreviated notation. The long notation is, in fact, is like this: AP plus 1, AP plus 2, and so on. Okay, so where AP is I'm going to write equal here. Where is this? Okay, so AN appears as if it is just a single object, but it is in fact a list of numbers. That's what the sequence is. It is a list of numbers that happens to be infinite. Sometimes we look at finite sequences and finite lists, and it will come up later. But at this time, we're looking at sequences that are infinite. We just typically omit that word. So infinite. Okay, so as examples, once again, it is let's just have a bunch of examples. It could be constant. That's a sequence. Okay, so AN is equal to 1. You can have a growing sequence. AN is equal to N. You can have a declining sequence. AN is equal to 1 over N. Okay, then we have those two sequences, arithmetic one and say 1, 2. Well, we already have this is arithmetic. This is arithmetic progression. We just happen to add one unit at a time, or one. So we start with 1 and you add 1 at a time. Multiplicative will be, or rather, the geometric progression is this: 1 half, 1, 2, 4. I multiply by 2 every time. 8, 16, 32. What's the formula?
X squared, N squared.
No.
Let's do.
Well, let me write n's for you. So these are ANs.
2 AN minus 1.
2 to the n minus Well, it depends on where you start, but I won't start with 1. So then yes, 2 and minus 1. Okay, so ands are these. So since I decided to start my counting with 1, then the first one should have n minus 1. That's where I have n minus 1 counting. But every time you multiply by 2, that is the ratio of the sequence, what's called the ratio of the geometric sequence. You keep multiplying by a certain number, and that's what we see here. You certainly can see something more interesting in the sense that there's a trend. Remember, that's our main interest is looking for trends. What's the formula?
1/2 to the n minus 1.
1 over 2 to the n minus 1, or if you want to make a point that this is a geometric progression, it is 1/2 to n minus 1. Okay, so if this is once again multiplicative. So unlike the first line, imagine this line. Imagine that you were doubling your money every year. On the other hand, if you're losing half of your money, that would be the next one. Okay, 1/2 or 1/2, 1/4. It's more typically you might be talking about, say, maybe population growth versus population decay. Okay, so population might be, usually you don't get the numbers multiplying by 2, like that magnitude, but it is usually happening in proportional manner. So, for example, per 1,000 of population, you would get, say, 30 newborn, or newborn minus the number of people who have died. That will become proportional. So, for like I said, for every 1,000 of population, you add 30. Okay, which in other words, you have a 3% growth of your city. But if you have more depth than births, then you have the same thing, and you have minus 30. Okay, so in this case, you multiply by 1.03 every time, right? So recursively, your population grows by 3% every time. You multiply by 1.03 every time. And if you lose 3% over there every time, what do you multiply by?
0.97.
0.97. That's how you lose 3%. You multiply by 0.97. Okay, so it's both of them are geometric progressions, except in the former case it is exponential growth, and in the latter exponential decay. Okay, so the latter is more interesting because we talked about that last time or the time before. There is a trend. If you're losing 3, or it doesn't matter how little you're losing every time, if it is proportional, or if you wait long enough, you have zero, not literally zero, but the population will dwindle to nothing or next to nothing. Okay. On the other hand, the trend is the exact opposite. If you have growth, ultimately there is no limit to it. You have as much money or as population as you want if you are prepared to wait long enough. Okay, so certainly the behaviors might be more complicated. Say, how about 1/2? Okay, there's a 2/3, 3/4, 4/5, 5/6. The formula? Look at the numerator and denominator separately.
N over n plus 1.
N over n plus 1, that's right. N over n plus 1. Okay, so do you see trend? If you put numbers there, the trend becomes quite obvious. So I didn't want to run Excel right now.
It's getting closer to 1.
Yeah, the trend is 1, so it's growing, but unlike the previous example of exponential growth, it slows down and it cannot never possibly pass 1. Right? Think about it. The numerator is always smaller than the denominator, so it cannot pass 1. On the other hand, n and n plus 1. Imagine that n is a very large number, say 1,000. Okay, then the numerator is 1000, the denominator is 1001. Okay, so we have 1000 and 1001. It's a number that is smaller than 1, but very close to 1. Okay, and you keep going, you replace 1000 with 1 million, the difference is, once again, or the ratio is even closer to 1. So the notation that we use is this. Okay, we will going to be talking about limits shortly, but let me just put the informally what we observe from what we see, the trend, and it appears to be this is 1. This one appears to be 0. This appears to be infinity. This appears to be 0. Once again, infinity. And 1, well, 1 doesn't go anywhere, so it is 1. Okay. So there are more complex situations. Sometimes it is hard or impossible to identify what the trend is, and so that's why we need all kinds of analyses. Well, let me give you one more example that is kind of important. Here is an example. 0.9, 0.99, 0.999. Okay, so it doesn't really matter what let's ignore the formula itself. It might be hard to guess it right away. But can you say anything about this sequence?
It's been the 1.
And it's also going toward 1 here. Okay. In fact, that is this is the meaning of this sequence is the meaning of 0.9999 . So a decimal with n repeated infinitely many times, the meaning of this sequence, the meaning of that decimal is 1 and only. It has to be understood as a sequence. Okay, and that sequence is there. Okay, and the limit of that sequence is 1, and that is why 0.9999 is equal to 1. Okay, so that's the meaning behind that notation that we do usually, we use informally in calculus kind of, but if that's certainly one of the reasons for studying calculus is that things like that get explained. So this is the meaning of, will be explained eventually. This is the meaning of infinite decimals. Infinite decimals, we have infinitely many terms there, so how do we get a grip of it, and how do we understand what that kind of number is equal to? Is it even a number? Maybe not, but certainly this one is, and it is understood as a sequence of numbers. Each of these numbers, look at the sequence, those numbers are unquestionably easy to understand. Like 0.9, it's a simple fraction, right? And if you keep going, then you have unfortunately infinitely many terms in the sequence to worry about. So you have to, or you could replace it with the limit, whatever the trend is, and we'll see that the trend is 1, and that is the meaning behind the infinite adjustment. Okay, one more example of. I want to, well, this is let me illustrate this, what I have here. I put n. So visualization is a kind of important. So this is y equal to 1. And I could plot these 0.9, 0.99 like this. Well, probably even goes faster than that. You have to put the equal intervals between them, like this. Okay, so if you plot enough points of this kind on the graph, they will be virtually distinguishable from that one. So they almost merge. Okay, so that is the meaning of the limit. So when the plotted points become well, there is virtually no change. Look at this. So even though there is certainly some progress, but that progress becomes smaller and smaller, and it never passes 1. Right? 0.999 doesn't matter how many 9s you have. it can never be larger than 1, so that's the, you have, on the one hand, you have growth, and on the other hand, you have the ceiling, okay? So that is the typical situation when you end up with something meaningful. So there is a trend there, well, I guess we need an example when there is no trend. Can you give me an example with no trend? What do you think it should look like? Something that has no trend. In this sense, look at this picture, and we'll try to think of something that does not look as how should I say? I mean, you can see it stabilizes. So imagine that something that does not stabilize as we move to the right.
Just something with random data, like say you try to plot a survey or something, like say
Well, what you're saying is that typically data has no trend. You don't expect to have a trend. So if you collect data every day, say temperature, you report it every day, it's not going to progressively. There is no trend whatsoever. That's true, but I just want to have a mathematical formula for such a thing. So if you can, let me suggest something, and then maybe you can think of a formula. Like this, so something that continues to go up and down. What do you know about graphs like this? That go up and down.
Trig function.
And it's trig function, specifically this is probably sine, so where you could pick sine, so an equals sine n. It will have no trend. Okay, so to make that point, let me run Excel finally and see if maybe I have some, well, maybe I can. Well, that's not open. Okay, we can try to open it. So, okay, so what's okay, so so I have some here. There's let's say maybe so Excel does a good job visualizing it. So here's one sequence. So this is the sequence. Let's take a look at the formula. So ignore X. This is what we're talking about. This one is. Oh, that's a good sequence, but not especially simple one. So let's see. Like I said, ignore X. It doesn't contribute anything. But can you see the formula? It is a recursive formula. So the blue, the previous entry, the previous term of the sequence is, and we add a new IN number. Okay, and that new number is, you see what it is? 1 over FACT stands for factorial. You know what factorial is? The factorial? Well, we'll talk about that later. It is simply the product of numbers from 1 to n. So n factorial is 1 times 2 times 3 and so on times n. Okay, so I guess you just didn't pick the better one. It's like this, so we'll get to that at some point. Here's another example. This is a pretty good example that the trend does not have to be from one direction. So it could go up and down, and the trend is still clear, right? You can see how the behavior stabilizes on right. Okay. On the other hand, also keep in mind that frequently the interpretation of our sequences is dynamical. They're just like with that simulation of the solar system. In other words, the value of n is invisible. This is, you can see on this table that these are n's are on the x-axis. These are n's. and the values of the sequence are along the y-axis. But if you look at those red ones, they are actually the values of just the values, just the values of the sequence without the value of n. And you see the what the pattern. If you just ignore the blue ones, look at the red ones. Do you see what's happening there?
I'm not saying all in one.
They're denser. Around one, they're getting denser and denser. If you plot more points, they will become really dense, and you see how loose it is away from one. Okay. So this is sin m. No, that's not sin m. This is actually look at it. It is the formula. It's sin n over n. So in spite of the oscillation, division by n. It's not an x, it's n actually, makes the swing smaller and smaller. And then once again you have a trend, you have a limit, and it is equal to 0. Okay? This one, an interesting example. So what do you think about this one? In terms of the trend? Two trends, yes, that is what you see, because there is one kind of branch stabilizing towards whatever it is, 2.3, and the other one 1.7 or something like that. But that we actually reject it and say this one has no trend, because just like sine, it goes up and down. This is what it does, exactly the same thing. It goes up and down, even though there is some kind of a stabilizing picture to this picture, but actually we are not skipping. We cannot skip from top to bottom. We always go up, down. So the oscillation never does that, and that's why this one has movement. Okay, so these are the reciprocals. 1 over n. That's simple. This is sine 1 over n. Okay, so this is the bank growth. Arithmetic progression. So you start with 1,000. So this one is defined recursively. We increase the size a little, and you can see, well, the formula that unfortunately doesn't get bigger. So you increase your amount by $20 every month. Okay, that's what the formula is, and you can see how the end result is straight line. And you apply from recursive formula. It's very simple if you just highlight this. See, as all you need to do is to know the previous amount, say 10, 20, and then you add 20 more. Okay, and then you keep computing, and then this is the graph. And this is just more of it. This is an interesting example. It's not only there seems to be no trend, in fact, it behaves very erratically. It looks random, even though there is very, very simple and very deterministic formula. This is the formula that we use, and we compute it, and it appears that it has whatsoever no particular behavior whatsoever. But it is actually there's a parameter. So you see the formula here. It is the first is parameter that make it bigger again. Okay, bigger. Okay. So if you look carefully at the formula, what it does is it takes the previous element and it appears twice. So it will be like x times 1 minus x, but also multiplied by that number in the beginning, which is the parameter of this. It's called the logistic sequence. Okay. So I can change this parameter and say 0.1. And the behavior is entirely regular. Well, let me go through these. 0.3, 0.8. Okay, so it's still very, very regular. 1, still regular. 1.5. It is not going to 0 anymore. It's going to, let's say, 0.3. And then things are changing slightly or not so slightly. At 2, it is constant to begin with. Okay? 2.1, Still okay. Still okay. 2 point. At some point, there is some interesting stuff to start to happen. I just can't remember at what point exactly. 2.8. See how it starts to oscillate. Oscillate, but the oscillation dies out. So one more time, more oscillation, still dies out. But if I put 3 here, well, let's see. You see that it's broken up. So one sequence pretty much has all possible behaviors here demonstrated to you. So this one, you can see that it's just the same example that we saw a minute ago. So so even though there seems seemingly 2 trends, but at the end of the day, it is 2 trends, and they're always separated, and there is no one pattern of behavior. And then at the end of this process, we end up with something like that. It starts to become more and more random, right? And at some point, might be there, and then again, it starts to converge. Okay, so so these are just the examples. I want to do one more, however, and that is more dynamic. So this is the advantage of this. Is certainly we can see the whole thing. No, this one. We can see the whole thing, right? The whole sequence is visible, right? But it's interesting to think in a more dynamic way, just like with the simulation of the solar system. Okay, so I have somewhere another simulation. Okay, it was the recursive. Yeah. Yeah, so recursive ones require circular references, which is that recursive formula that we had. This is what we saw on Monday. And the formula that we saw is Excel understands it, unfortunately, as this one, the one in the middle, understands it as self-referential. It is self-referential, except there's just really no problem with that. You just compute one, and recompute. Okay, so when you do that, the unfortunately Excel needs to be, I think it needs to be. You see, it's not working because it does not understand the recursive nature of the reference. Okay, so I'm supposed to allow, enable, I think that's there you have to go somewhere and allow the self-referential things. Okay, let me try this. This work. Yeah. Okay, so then this would be so on Monday. Okay, so but that's not what I want to show you. Here's the deposits. So once again, that example of when you deposit a constant amount of money every month. So so this is, look at the 2 graphs. One graph is on one graph on the left shows you the dependence of the amount of money on, and it gives you the whole thing like this. Okay. On the right, all you see is the dynamic, so it goes up at a constant speed. Okay, so and if we continue on, we create the whole sequence on the right. Okay, this one is the compound interest, the same story. So you can see the exponential growth instead. So it's not straight anymore. It's going up and up and up. Logistic, and this is the logistic we just saw. Now let me start over. And once again, this is the randomness of the behavior. Look at how random it is. So it is totally unpredictable as to what, if you know where you are with your money or location, if you know where you are, say the moon is located, you know where it's going to be the next moment. Everything seems all right. But when some sequences, such as the logistic one, as you can see, look at those sequences on the right especially, is very, very revealing that every jumps back and forth, and that is incidentally is frequently the way we describe the behavior of or at least we illustrate the behavior of things such as stock prices, for example, or any kind of prices. They behave in a seemingly random way. Okay, they go up and down, and it might be very hard to actually establish and point out the causes of those fluctuations, and the trends might be seen, like months afterwards, and you realize, oh yeah, there is a trend, but actually it was going up and down so wildly that it was, at the time it was impossible to recognize. So, and it's not because of the randomness of the life or some special complexity of life. The sequence is very simple. This sequence is very simple, the logistic sequence, but it's just the chaos appears from regularity. So you apply the same very simple function in a recursive way, and the next step is it becomes unpredictable because of the, I don't know why, but it just happens. So just because we know the past and we know how, and we know the dynamics, how it progresses, doesn't mean that we can predict the future and beyond any kind of short period of time. So that's the thing about it, about nature. Okay, so let's see. So with all these examples, now it's time to actually define the limit of sequences. Well, let me actually go back here and just show you not this one, but say maybe this one. Look at the numbers. I want you to see that the numbers are actually, if you ask yourself what is the trend, just look at the numbers. So these are ants over here on the left, and on the right we have our values. And you can see how close and closer they're becoming to each other. You don't really have to move the graph. You just go on, continue with this. If you go on for long enough, it will work out. Okay, now let me pick another one. No, this one. No, this one does not converge. This one. Okay. So if you compute enough values, I'm doing the right thing again. Unfortunately, I have to make it more complicated than it deserves. Well, so I hope it is clear enough how from the numbers you can recognize the patterns from nothing but numbers in the, it is just icing on the cake is the graph on the right. If all you want to know is there a trend of convergence, you can see it simply from numbers. Okay, so yeah, I guess we'll just start next time with definitions. It is time to make this more specific, and so we can actually do algebra with not just numbers, not just pictures, but we can do algebra. We can have sequences. We can find whether they have limits or not. We can do algebra. Then we can add, subtract, multiply, divide sequences, and ultimately maybe prove some theorems. Okay, so I'll see you Monday.